That's the basic idea. One of the benefits, you can have functional elements resulting in modular components. So I have modular components now. Come up with a new sensor. I can add that to the data bus as long as I have defined common interfaces. I don't need a connector into the FADEC. There's commonality, expandability, scalability, flexibility, all that stuff. You have obsolescence mitigation. As new versions of sensors come, new electronics come, you can put that more easily. You reduce the processing requirements for the control box per se, and you can reduce the weight. There are trade-offs. You're adding more weight because you're adding electronics closer to the sensor. You're reducing the weight because you're taking the wires off. So whether you have a lower weight or the same weight is really a function of how big the engine is. Bigger engines, you have more of a weight gain. Smaller engines, you might not see any weight change. But long run, operability-wise, you have reduced costs because you have increased the diagnosability of the system. And the thing is, if you use open system standards, then you can leverage all the progress being made by each component manufacturer. You're not tied in, when you certify the engine, you're not tied into a pressure sensor of a certain kind from a certain industry. Well, you can take anybody's pressure sensor with a common interface and you put it in there. So that's the idea, right? Right now, if you add a different one, you'll have to recertify the component. Okay, so how do we move from there? This is the current situation. Electronic control unit located on the fan casing. I'm showing a commercial version with all the bundles of wires going to different places. So what we are working on right now is, let me just go to the listing. What we have done at NASA Glenn is working in collaboration with the Air Force, Army, Navy, and engine OEMs listed here: GE, Pratt & Whitney, Rolls-Royce, Honeywell, the engine OEMs in USA. System integrators in the USA, Hamilton, BAE, and suppliers like Woodward, Eaton. These are the ones who supply the control components, the sensors, small businesses who work a lot of sensors. We have created something called a distributed engine control working group. So the idea of this control group, working group is to identify what are the key areas that we want to invest in right now to enable a future roadmap of infusing this technology into the future engines. So the idea is that this organization identifies, and the funding that comes from the government agencies can now be geared towards those targeted advancements. So, going back, in the 5 years, the idea is to develop electronics such that you can break down the FADEC into two pieces. One would be a data concentrator. So that is basically, you're still taking all the analog data, and this is where you process it, do the signal processing, and you convert it to digital, and then you put it in a bus for control law processing. So the control law processing is still done in some kind of a box. And this control law processing box, now you can put anywhere you want. You can put it even on the aircraft if you want, right? So that's the first thing. But in order to do that, you need a little higher electronics. Right now, electronics that you have for FADEC is 150 degrees C silicon electronics. So there is work being done in silicon and insulator electronics, which will allow you to operate up to 250 degrees centigrade. So you can put this box a little closer in a little hotter environment. But this will be a smaller box. There will be one small box here, so you reduce the harness weight and stuff. And you're still using the legacy sensors and actuators. You're still using all the legacy control stuff. So recertification or whatever it's an evolutionary movement. And the 10 years would be transitioned to a network control architecture where you still have a compact data concentrator where you might still have a data concentrator and a separate control box, but you would have moved to a digital data bus with more electronics with sensors and actuators. So you can have greater than 300 Celsius electronics. And ultimately, 15 years, the idea is that everything is on a data bus and the whole control processing, signal processing would be in a box which is even on an aircraft. So you can even have down the road wireless capability where you don't even need the data wiring, especially for functions which are only for diagnostics. You're not using them for control. You can use wireless sensors because for control there is still the issue of security of your communications. So that's the idea of this architecture. Skip that. Like I said, there is a working group. So what are the technical challenges for this? There are several tall issues. One is the high temperature electronics. So that is already there. You need high temperature electronics, and I believe there is a consortium in Europe working on distributed engine control electronics, high temperature electronics for distributed engine control. Does anybody know about that? European consortium? Okay. That's one of the things I've tried to figure out, how we get the Europeans and the Americans to talk to each other so we can have some collaboration. That's the whole idea of NATO alliance, right? So I got to find out more about that. Another one is communication pathway from FADEC to engine system. What are the bandwidth requirements and how is it affected by the engine environment? You have digital data buses currently in controlled systems on the aircraft, but they're not there to, those data buses are not suited for performance on the harsh environment in the engine. So are there commercial data buses which you could apply to this environment? Power distribution, okay, you're gonna have actual electronics in separate places. How are you gonna do this power distribution to all the electronics? Right now, all the electronics is in the FADEC, so your power distribution is concentrated in the FADEC. So how do you do the power distribution? System functionality. Now you're gonna have your distributed control basically. So logic-wise, how do you make sure everything works together? And system modularity, ultimately, how do you define the common interfaces? How do you change the certification paradigm to be able to just plug and play with new pieces? So all that stuff is to be done. Our focus has primarily been focusing on the electronics right now because that's the big driving force. If we can get to 250-degree electronics, then you can get to the phase one where you have a data concentrator and a control processor.
I think getting to standards, if people agree, is the one thing that's a big issue, isn't it? Particularly in the communication side.
That's the big issue in communication, is the interface, having typical standards for interface. That has to be developed in consultation with everybody. But that's part of this group's job. It's like herding cats. We got 20 organizations. Each one has their vested interest, but they all are smart enough to realize that nobody's going to make progress unless they work together. There's not enough money for everybody to play their own game. And the way it is seen is the OEMs. The OEMs don't do this electronic stuff by themselves. Even the FADEC is built and programmed by providers. The logic that goes in FADEC is developed by the OEMs themselves. They won't outsource that. But actual control components are all built by providers. BAE, Goodrich, Hamilton Sundstrand. So they're all going to buy from the same people. So it's their advantage to work together.
And the 250 was F or C?
C. That is all 150 degrees C is current, 250 degrees C. This 145 degrees for thermal F, I just learned recently. But it's very important to say that is F. I don't know why. But they say you have to have enough margin in that. It cannot be hotter than that. The fuel is hotter than that, then you are not assured of your electronic stability.
There are concepts, at least in military, to go for much hotter fuels.
Yeah.
That will again change the game.
You cannot go to hotter. Right now, that's the driving.
For the military.
For the military. And commercial, there's not so much of heat dumping into the, I don't know, because there's a huge fan, you have a lot of air to cool.
We're at the limit.
For
Civil's at the limit of fuel temperature as well.
The civil?
Yeah.
It's also the fuel. But FADEC is not the limiter factor for fuel. Something else might be the limiting for the fuel temperature.
There is an issue with the fuel, as far as I know, exceeding certain temperature might start changing the structure. Because fuels are pixel perfect.
Yeah, but the
You can
controls,
pick them up, yeah.
the control, FADEC is not, FADEC is air cooled.
Yeah.
So FADEC is not contributing to whatever the limit of this thing.
The fuel, it's because itself, you can't
Yeah.
heat it too much up.
Right.
That's all.
Right. That's the other.
You're going to smaller, faster cores. You can
Yeah.
have civil product.
Right.
Putting more heat into the oil.
And
You've got to
most
put it
of the
somewhere.
heat to the fuel comes from the oil.
Right.
Right.
Cooling
Cool
the
your
oil.
you
Cooling the
use
oil.
the typically use the fuel.
So there are other factors driving in the commercial. In military engine, FADEC temperature limits the amount of heat you can dump into the fuel. They want to, the thermal management guys don't want to dump more heat. So that's now, so we told them, hey, listen, then you got to work with us and convince the senior people that, hey, listen, in order for us to dump more heat, we need to get rid of this control box.
You don't have this limitation all the time. Typically in military oil and fuel systems, you only have a few flight conditions that give you the limitation. So if you are flying low altitude, hot climate, high speed,
Right.
then you don't know where to go with all your heat. Yeah?
Similar with civil, there's just particular pinch points
Yeah.
that they do
Yeah.
drive to
They
design.
limit
Yeah.
to
For civil, the limit is, civil and military also is on ground. Firing up the engine on ground because there is no air going through. So that's a driving factor of your electronic design is how much you can still accept. But the whole idea is, we got the thermal management guys to say, yes, we want to help you guys get rid of the centralized FADEC control box. So we asked them to quantify as to what would be the next limiter, how much heat they can dump more if they did not have a 150-degree limit for the FADEC.
for persons who are interested in this stuff, it might be worthwhile to look up the proceedings when they come out of the symposium that has now been in Bucharest.
Of course, that was a thermal
Bucharest was
management.
on thermal management of vehicles, and there were several presentations on this
Okay,
part. Of,
very good. Good, we should look into that. So, per se, if you want to change the architecture, you don't really need any new sensors or actuators. You can use the current sensors and actuators. But what you need is onboard electronics located close to sensing elements, and actuator effectors to process signals and enable network communication. So now you've got to think of how do you integrate electronics with the sensor close by. Requires high temperature capability, and you need to figure out innovative power supply architectures and technologies to be able to power these electronics, which are now located. Right now there's a centralized production and power control. Now you've got to figure out how you're going to get the power to these. So